Hello everyone and welcome. We are excited to introduce our advanced USB4 verification IP. Let's take a look at how it can make your design and verification process easier and more efficient.
Before we dive in, let's take a moment to consider the importance of USB4 technology. With the growing demand for higher data rates, seamless connectivity across multiple devices, and backward compatibility with existing USB standards, USB4 is becoming a key player in ensuring efficient communication in today's high-speed environments. At TrueChip, our USB4 VIP offers a seamless plug-and-play interface, supporting both IP and SoC integration. This means it's designed to make the verification process smooth whether we are developing a standalone IP block or integrating the protocol into a larger SoC. One of the primary challenges in modern day verification is handling the increasing complexity of connected devices and routers. Our USB4 VIP supports various device, retimer, and hub configurations at different depths, making it versatile enough to handle a wide range of scenarios. Let's talk about one of the standout features, backward compatibility. Our USB4 VIP supports USB 3 and USB 2 protocols, ensuring that even as you transition to USB 4, your older devices and systems will still operate efficiently. This is crucial in industries where legacy systems are still in use and must communicate seamlessly with newer technology. For instance, think about a scenario where your system is communicating with older USB 2 devices while transmitting data to a new USB 4 router. Our VIP ensures that this communication remains efficient without any loss in data integrity or speed. Moving on to some of the advanced features, our USB 4 VIP supports Gen 4 speeds, which includes speed up to 80 Gbps in symmetric and 120 Gbps in asymmetric lanes. This means that system can adapt to different configurations and bandwidth requirement on the fly, which is particularly useful in environments with varying data loads. It's also backward compatible with maximum of 40 Gbps in Gen 3 and 20 Gbps in Gen 2 modes, giving the flexibility to work across different generations of USB protocols. Beyond speed, one of the critical elements of USB 4 is tunneling. USB 4 supports tunneling traffic types like USB 3, DisplayPort, and PCIe. It also supports bidirectional and unidirectional interdomain connectivity, Thunderbolt TBT3, and TMU block with STLP mode for greater flexibility in data transfer. This makes USB 4 a powerful choice for applications requiring multiple protocol support, such as docking stations where video and data transfer occur simultaneously.
Now let's take a look into the key differences between USB4 version 2 and version 1, which are USB4 v2 supports maximum data transfer rate of 80 Gbps while version 1 of 40 Gbps. USB4 version 2 port operates as an aggregated link, that is symmetric or asymmetric link, whereas in version 1 it operates as single lane link or dual lane link. USB4 version 2 supports PAM3 and PAM2 signaling, whereas version 1 supports PAM2 signaling. USB4 version 2 supports host interface reset and host router reset, while version 1 supports only host interface reset. And additionally, version 2 supports enhanced unidirectional handshake mechanism along with unidirectional and bidirectional handshake mechanism, which are supported in version 1.
Let's take a closer look at the architecture of TrueChip's USB 4 VIP. The VIP is comprised of three primary components: the host on the left, the monitors in the center, and the device on the right. Communication between the host and device takes place over USB 4 Type-C connections. Both the host and device are organized into several layers, including the protocol adapter layer, configuration layer, transport layer, and logical layer. Additionally, the host features a connection manager and a host interface adapter layer, which are responsible for managing path setup, routing, and controlling data flow between devices. The connection manager plays a key role in enumeration. When the lane adapters transition into the active state known as CL0, the host lane adapters notify the connection manager that the device is connected to the downstream facing port by sending a hot plug packet. Upon receiving the hot plug packet, the connection manager enumerates the device by sending control packets, establishes the path between the host and device, and initiates the transmission of tunnel data over the configured path. The monitor component continuously observes the entire communication process between the host PFM and device PFM, ensuring proper data flow and protocol compliance. Now let's delve deeper into the logical layer and sideband of our VIP. Our rich set of configuration parameters allows you to optimize both logical and electrical layer functionalities. This optimization is essential in fine-tuning performance depending on your specific system needs. One feature I'd like to highlight here is the support for low frequency periodic signaling across Gen 2, Gen 3, and Gen 4. LFPS plays a pivotal role in lane training, ensuring that data lanes are properly aligned before transmission begins. This ensures reliable data transfer even in challenging environments where signal degradation might occur. Moreover, our sideband system supports various transaction types, including administrative transactions, broadcast and address retimer transactions, link transactions, and extended link transactions. Each of these transactions is crucial for ensuring efficient communication across different layers and components, especially in complex designs involving multiple devices and hubs. One of the cornerstones of reliable data communication is the encoding process. Our USB4 VIP supports advanced signaling mechanisms such as Gen 4 PAM2 and PAM3 signaling, ensuring high-speed, reliable data transfer across different lanes. We also provide robust encoding mechanisms, including binary to ternary conversion and RSFSC block with RS 504,480 for Gen 4, offering 12 error corrections. For Gen 2 and Gen 3, we support RSFSC block with RS 198,194 with 2 error corrections and lane bonding support. These features ensure that data integrity is maintained even in high-speed communication environments where signal errors can occur frequently. Another critical aspect is lane management. Our USB4 VIP ensures that lane initialization is handled efficiently across all generations, including Gen 2, Gen 3, and Gen 4. We provide full support for phases 1 through 5 initialization, ensuring proper setup before data transmission on either symmetric lanes, which is pair of Rx and Tx connected with other, and asymmetric lanes, which is 3 Rx and 1 Tx connected with 3 Tx and 1 Rx. Additionally, the system supports scrambling and descrambling for Gen 2, Gen 3 and Gen 4 with PRBS 11, PRTS 7 and PRTS 19 generators, helping maintain signal integrity and minimizing the chances of errors during transmission. Our lane adapters and sideband also include various bypass mechanisms allowing for robust lane management and adaptation to different system conditions. Moreover, with features like skew and deskew management, our VIP ensures proper lane alignment even in cases where multiple lanes are transmitting data simultaneously. This helps avoid data corruption and ensures that the system operates smoothly across all speeds. Lastly, I'd like to highlight our support for Gen 4 logical layer training sequences, including TS1, TS2, TS3, and TS4 order sets, as well as order sets such as Ignore, Unbound, TSQ, and TSNOS. This ensures that the system can handle all necessary training operations regardless of the link configuration. Our power management support includes states like CL0S, CL1, and CL2 along with respective objections. This helps in optimizing power consumption without compromising on performance, especially in low power devices or battery operated systems.
Let's explore the advanced transport layer features of TrueChip's USB4 verification IP designed for efficient packet handling, routing, and reliable transmission while meeting USB4 standards. TrueChip's USB4 verification IP offers high configurability with a wide range of parameters and callbacks, supporting various packet types like tunneled, power management, link management, and control packets. This ensures versatility for diverse USB4 applications and dynamic system requirements. The VIP efficiently manages routing tables for ingress and egress adapters, maintaining strict packet sequencing for data integrity and reliability. Bandwidth arbitration and priority scheduling allow critical data to be prioritized, while support for four flow control buffer schemes flow control, dedicated flow, shared flow, and restricted shared flow ensures smooth data flow and congestion prevention. TrueChip's transport layer is adaptable across generations. Gen 4 eliminates minimum packet gaps for continuous data flow. It also adheres to standard packet formats, employing HSC and ECC to safeguard data integrity during transmission. The IP offers flexible payload padding options supporting 0-byte or user-defined padding and also user-controlled linear scaling factors to accelerate simulations. The transport layer works seamlessly with the logical layer to ensure efficient traffic management without compromising performance or USB4 compliance. Today, we'll explore the comprehensive features and capabilities of our VIP configuration layer, which offers a broad array of configuration parameters and callbacks. These tools provide precise control over the configuration layer functionality, allowing you to customize the system to fit specific requirements. Our VIP excels in managing a diverse range of control packets. This includes read and write packets for data access and modification, notification packets for status updates and error reporting, hot plug events for device management, and interdomain requests and response to facilitate communication across domains. We support a wide spectrum of notification events such as link recovery, HSC, errors, link errors, and asymmetric links. The VIP also handles the acknowledgements for these events, ensuring that any issues or status changes are effectively managed to maintain system stability. Reliable routing of control packets is crucial for effective communication and data integrity. RVIP incorporates robust mechanisms to ensure accurate and efficient routing of these packets, preventing errors and ensuring consistent performance. Advanced features of RVIP include critical reset functions like downstream port reset and host router reset. It also supports router enumeration and includes a bypass mechanism for flexible routing configurations. The VIP adheres to standard timers and offers user-controlled linear scaling factors, allowing for both faster and more detailed simulations as needed. For thorough testing and debugging, our VIP supports error injection in any control packet, enabling detailed testing of error handling and system responses. Additionally, we use TrueEye, our GUI-based transaction analyzer, to provide a visual interface for analyzing and troubleshooting configuration layer transactions, enhancing your ability to diagnose and resolve issues. Now, we'll dwell into how our USB4 connection manager ensures reliable communication, efficient bandwidth allocation, and robust error management for seamless USB4 operations. Our connection manager facilitates efficient control packet communication, enabling smooth transmission of requests and responses between the host and USB4 devices. through the host interface adapter layer. It also excels in detecting and resolving loops within the USB4 domain spanning tree, thereby maintaining a stable network topology. Dynamic path management is another key feature supporting the setup and teardown of paths for tunneling various protocols such as USB 3, PCIe, and DisplayPort. This flexibility optimizes bandwidth utilization across different protocols. Our system efficiently manages bandwidth and credit allocation across multiple clients including USB 3, PCIe, and DP, ensuring fair distribution throughout robust credit management mechanisms. In terms of error handling, the connection manager promptly detects and addresses link errors using notification and acknowledgement packets. Control packet management is handled seamlessly, encompassing tasks related to enumeration, configuration, and overall management of the USB4 domain. For port management, the connection manager supports features such as lane bonding, asymmetric link transitions, and resets, ensuring adaptive management for Gen 2 or Gen 3 speeds. The VIP also offers inter-domain functionality, allowing cross-domain connections without the need for lane bonding, enhancing system flexibility. Additionally, power management is optimized with efficient handling of low power state transitions, lane enable or disable mechanisms, and sleep or wake cycles. This comprehensive approach ensures optimal performance, adaptability, and resource efficiency across your USB4 network.
Now, let's take a look at TrueChip's host interface adapter layer. Our VIP supports transmit and ring descriptors, enabling efficient control packet flow and host-to-host tunneling. The connection manager ensures reliable control packet transmission and reception, maintaining data integrity. We offer customizable descriptor ring modes and feature end-to-end credit-based flow control to manage data flow. The system also supports interrupt handling, user-controlled options, and scalability for path configurations and ring size and data buffer size in line with USB4 specifications.
Now, let's turn our attention to the Time Management Unit (TMU) within our USB4 verification IP, which is key to achieving precise time synchronization across Gen 2, Gen 3, and Gen 4 links in both symmetric and asymmetric setups. TrueChip's TMU supports time sync handshakes in bidirectional, unidirectional, and enhanced unidirectional modes, facilitating both intra-domain and inter-domain synchronization. It accurately computes critical parameters like time offsets, frequency offsets, and host router time, ensuring precise alignment even in complex multi-device environments. The TMU handles TSNOS packet transmission for timestamp generation and asymmetry correction, and fully supports essential time sync messages, which are delay request, delay response, and follow-up, enabling smooth communication across devices. With strict timing gap and timeout management, TrueChip's VIP ensures reliable synchronization across multiple domains, allowing parallel execution of handshakes. Additionally, the TMU supports the transmission and reception of serial time link protocol packets at configurable intervals for real-time synchronization monitoring. Our VIP's architecture allows multiple hubs to be generated at individual depths within a USB4 domain. It supports all USB4 transfer speeds including Gen 2, Gen 3 and Gen 4 with both symmetric and asymmetric link configurations. The hub maintains active USB 3 DisplayPort and PCIe links across connected upstream and downstream protocol adapter layers. It supports multiple protocol adapters for USB 3, Gen X, Gen T, PCIe, and DP. as well as packet forwarding to the relevant downstream protocol adapter layer. Our hub supports default control and interrupt endpoints, providing USB 3.x host controllers with key information regarding the hub and its ports. Furthermore, it supports hub-specific control transfers like gate hub descriptor and gate port status. The USB 3.2 hub operates at up to 20 GT per second in single or dual lane configurations and communicates with adapter layers through the pipe interface.
TrueChip's Gen 4 hub supports pass-through for USB 3 Gen 2 tunneling. It also supports a configurable number of transmitters on the upstream and downstream ports in asymmetric mode. It supports all TMU features for USB 4 hubs, including advanced time synchronization methods like bidirectional, unidirectional, and enhanced unidirectional handshakes for accurate and reliable timing. TrueChip's USB4 retimer is designed to ensure high-speed signal transmission within USB4 systems supporting Gen 2, Gen 3, and Gen 4 speeds, which plays a crucial role in maintaining signal integrity over extended distances. Our retimer actively participates in the lane initialization process from phase 1 to phase 5 and supports PXFFE negotiation in phase 5 lane initialization. Our retimer also manages various states including CLD, bit lock, forwarding and various low power states such as CL0S, CL1, CL2, ensuring efficient data transmission and power management. It also features a sideband register space accessible via sideband channel transaction addressed RT transaction. TrueChip's retimer VIP supports the retimer index updation mechanism using broadcast RT transactions. It is compatible with both symmetric and asymmetric configurations at Gen 4 speed. Additionally, the retimer VIP supports the corresponding clock switch flows for Gen 2, Gen 3 and Gen 4 speeds. Now let's take a look at our VIP's logs, which we have generated by running USB4 USB3 tunneling test case to demonstrate the flow of data across host, hub and devices. In the current environment of this test case, there is USB4 host, hub and USB4 device. They will tunnel USB3 traffic via USB3 protocol adapters which are connected to internal USB3 devices. Lane adapters initially starts in inactive state known as CLD state before data transmission begins. Transitioning this adapter to fully operational states involves a 5-phase lane initialization process to ensure reliable and efficient data transfer. In phase 4 of lane initialization, the lane adapter enters training state preparing for data communication. In phase 5 of lane initialization, the receiver locks and PXFFE negotiation is completed. This allows the lane adapters to transition into the active CL0 state, enabling data transfer. Once all the lane adapters reaches to CL0 state, the router sends hot plug event packet to connection manager, which initiates the enumeration of all connected devices. The connection manager sets up the path for USB 3 tunneling across host, hub and devices. USB 3.0 traffic can now be channeled over the established path. Following this, the protocol adapter initiates receiver detection for the connected internal USB 3.0 components via the pipe interface. At this stage, the respective USB 3.0 links have transitioned from the polling state to U0 active state. Since the purpose of this test case is the enumeration of the USB 3.0 hub, the HSCI controller will proceed to enumerate the USB 3.0 hub accordingly. Let's look into retimer logs. In the current test environment for this test case, the setup consists of a USB4 host, USB4 hub, USB4 device and a single retimer on each USB4 link. Initially, all retimer channel state machines and the router's lane adapters start in the CLD state. As the retimer enters phase 4 of lane initialization, transmitters and receivers are enabled. At this point, the respective retimer channel state transitions to the bit lock state. During phase 5, all ports perform TXFFE negotiation with their adjacent router or retimer. Once all enabled receivers detect TS3 and the corresponding transmitters complete TXFFE negotiation, Gen 4 clock switch flow is performed, then followed by transitioning retimer channels to the forwarding state. After all router ports reach the CL0 state, the connection manager proceeds with the enumeration path setup and then tunneling data transfer.
To give you a clearer picture, we will examine how data is transmitted and received on these links with the help of detailed waveforms. Let's begin by looking at the first image, which depicts lane adapter 1. In this scenario, we have data being transmitted and received on lane 1 between the host and the device. If you closely observe the waveform, you will notice how PAM3 encoded signals are handled. PAM3 encoding is crucial in achieving high-speed data transfer by efficiently representing data with three discrete voltage levels. The waveform illustrates the transitions and the encoding of these signals, providing insight into how data integrity is maintained across the high-speed link. Moving on to second image, which shows lane adapter 2. This image illustrates data transfer occurring on the second adapter.
While designing USB4 IP, one can face many challenges, so let's take a look at few of them. One key challenge is verifying the different components of the USB4 router, including the logical layer, pipe architecture, transport layer, TMU block, configuration layer, and the host interface adapter layer. Since USB4 integrates USB 3.x, PCIe, and DP adapters, the process needs to ensure that all of these work together seamlessly, including compatibility. For Gen 2 and Gen 3 speeds, keeping lane synchronization and avoiding signal misalignment during RSFEC when lanes are bonded adds another level of complexity. This challenge becomes even more important when managing routers connected at different levels or across different domains. USB4 verification is a complex process that requires a solid understanding of the multiple protocols involved, careful management of bandwidth, and ensuring that all devices meet the latest standards. These challenges make the verification process crucial and demanding, but also essential for successful USB4 implementation.
In summary, TrueChip's USB4 VIP offers comprehensive support for multiple protocols, speeds, and configurations. Whether you are dealing with legacy systems or working on cutting-edge designs, our VIP ensures seamless integration, robust performance, and efficient verification.